Hi, welcome to the video solution for past paper. This is Edexcel IAL Physics Unit 3, January 2020. So let's start. Question number 1. A student was asked to investigate how changing the temperature of a diode will change the potential difference at which the diode starts to conduct. Draw a label diagram showing how she could carry out this investigation using school laboratory apparatus. So in this question, you just need to draw a label diagram showing all the equipment used in this investigation. So remember, almost in every experiment or investigation of electricity that you deal with, major components are ampere meter, voltmeter, and the component to be investigated, and the component and the power supply that you will be using, maybe a cell or maybe a power supply, and then a variable resistor. These are most common equipment or apparatus that we used in almost every investigation. So the idea is we need to study effect of temperature. That means we need to heat the diode. That means it's all about heating electronic component, and most common situation we use water bath. And for water bath we use beaker in which we put our component and we change the temperature. So you can draw a sketch or a diagram, something like, you can say you have a beaker on a stand. This is a stand, a tripod stand maybe, or whatever. You can draw, a Bunsen burner, and the flame. You have a component inside, a diode. You can label it. You can use a symbol for this is a diode, and then you can connect it with the circuit. So the idea is you will have to maybe you can use ampere meter, and then you can do a power supply, something like this, and then you can connect a variable resistor, so to change the current or control the current, something like this. And then you can go back here, and then you can connect a voltmeter parallel to the component. So this is your voltmeter which is connected parallel to your component. And yes, don't forget to put a thermometer inside. So you can put a thermometer close to your diode so you can measure the temperature. You can label it something like this, and now you can label your diagram. So you can say that this is your diode. Voltmeter, ampere meter is already labeled. You can say this is a power supply. This is variable resistor R, and this is your thermometer. This is your thermometer, and if you wish you can measure this burner, Bunsen burner. Oh, that's how you can label your diagram. Part B, identify one safety issue with this investigation and how it may be dealt with. Clearly, the investigation or experiment involves a heating process. That means you should be careful when you are handling hot objects. So you must wear gloves and of course safety goggles because of hot water is involved. So, but generally, we say that because heating is involved, so make sure that you wear gloves or you use tong or clamp to hold some hot equipment. Question number 2. A student investigated the relationship between the mass m a boat can carry and the depth d below the water surface of lowest point of the boat. He modeled the boat using a glass beaker. He added 10 grams slotted mass and marked the position of the water surface on the beaker as shown. Okay, so this is your beaker and fine, radius of the beaker, depth, water bath. Okay, fine. The student assumed the beaker was a cylinder with a radius r centimeter and the water had a density of 1 gram per centimeter cube. Show that the upthrust U on the beaker could be calculated using the equation U is equal to pi r square dg 1000 divided by 1000, where d is in centimeter and U is in Newton. So clearly the situation is when you put the mass, then weight of the mass acting down, which is W, and upthrust acting on the beaker. So upthrust acting on the beaker in upward direction, and because beaker is floating, that means upthrust is equal to weight. And of course the formula for upthrust, U is equal to rho V and G, where rho is the density of the liquid or fluid in which the object is sinking or floating. V is the volume of displaced liquid or fluid, or you can say V is the volume of immersed object, and G is of course gravitational field strength or acceleration due to gravity, which is 9.81. So you need to do something that the upthrust can be rearranged in the form of pi r square dg. Clearly, if you see, d is the depth of the cylinder inside the fluid, and it is cylinder. If you see, this is cylindrical. So you know that volume of the cylinder V, which is inside the fluid, is pi r square d, and rho is the density, which is given as 1 gram per centimeter cube, but we need to give answer in Newton. That means it is better, instead of gram we say rho is 1 upon 1000 of kilogram per centimeter cube. Now let's substitute all the numbers here. So U is equal to rho is 1 upon 1000 kilogram, centimeter minus 3. V is the volume, which is pi r square d, because they are saying d is in centimeter, so we will be taking the volume of the cylinder as centimeter cube. So this is the volume, and g is acceleration due to gravity. Clearly you can see that centimeter and centimeter cube is gone, and only left is kilogram and unit of g. And unit of g, if you remember, this is acceleration due to gravity, which is ms minus 2. So this kilogram and this ms minus 2 becomes Newton. So finally you can rewrite this equation. U is equal to pi r square d into g divided by this 1000. That's how you can prove. Part B, the student marked the position of the water surface on the beaker for different values of m. He plotted a graph of d in centimeter against m in gram. Okay, so depth in centimeter against mass in gram. We have a straight line. When the beaker is in equilibrium, upthrust is equal to weight, leading him to the following equation. M is equal to rho pi r square d, where rho is 1 gram per centimeter cube. So determine the diameter of the beaker using information from the graph. So it's quite a straightforward condition. See, if you need to find the diameter, that means you look at the equation. M is the mass, d is the depth, where r is the radius. This is radius. So if you can somehow, if you can figure out value of r, then double of the radius is the diameter. That is your required, quantity here, required the diameter. So first you make the r as a subject. So you can see that r square is equal to m divided by rho pi into d, and rho is 1, so r square is equal to m upon pi d. Now you see here, let's see what is m upon d. If you see m upon d from the graph, so it's just for your information, m upon d is basically 1 upon gradient of the line. And why is that? If you see the line, this is the graph between d and m, and if I ask you find the gradient, so gradient of this graph or this line will be d by m. But in our formula we don't need d by m, we need m divided by d, which is 1 upon gradient. That means from the graph, if you can figure out gradient, then r square will be 1 upon pi times of 1 upon gradient. So meaning r square will be equal to 1 upon pi into gradient. That's how you can figure out radius, and then after taking a square root, you can double, and then you have your diameter. So let's find out the gradient. For gradient, I'm going to take 2 points on the line. So for me, the best points are, you can choose any 2 points as and you can make a triangle as big as possible. So let's see, I'm just taking this point here. This is 1 point, and coordinate of this point will be 170, comma, and this is 6. And yeah, this is fine. So the coordinate of this point will be 0, comma, 1.6. These are the 2 points. Now let's figure out the gradient. So gradient is y2 minus y1. Gradient will be y2 minus y1. That means 6 minus 1.6 divided by x2 minus x1, which is 170 minus 0. And then gradient would be equal to 0.0258, and you can round it off till gradient is equal to 0.026, and unit will be centimeter gram inverse. This is gradient. And now r square would be equal to 1 upon pi. Pi is 3.14 times gradient, and gradient is 0.026. So r square is 12.24 centimeter square. Taking a square root, r is equal to 3.49 centimeter. Clearly diameter is twice of the radius, so diameter is 6.99 centimeter. That is, d is 7 centimeter. This is the diameter of the cylinder. So I did this question in quite detail. You can skip definitely a lot of steps once you understand. Part C, the graph shows that the beaker would have a depth under the water surface with no mass added. Identify the source of systematic error and how it could be corrected. Clearly, if you see the graph on a previous uh, slide here, like here, so mass is 0, so you still have a depth. That means the students did not account the mass of the empty beaker. So the systematic error is mass of the empty beaker, so you should take care of the mass of a beaker and add it in a additional mass, and then you can plot graph and it should pass through origin. So that's how you can say that, because mass of the beaker did not consider, or it was ignored. So you must include the mass of the beaker, add it to the slotted masses, and then redraw the graph. Question number 3, a student investigated the refraction of light as it traveled into salt solution of different densities. For a salt solution, as the density increases, the speed of light in the salt solution decreases. She put a salt solution into a transparent semicircular container as shown. Semicircular container, ray box. Describe a method the student could use to determine the density of the salt solution. Nothing is given. Clearly, it's all about a solution. That means liquid. So density can be found using rho is equal to mass over volume. Mass can be measured through top pan balance, and V can be measured. It is liquid, so through measuring cylinder. So you can say that after measuring these two, you can find density using this formula. The student increased the density of the salt solution by adding different masses of salt. Sketch on the axis below a graph to show how the refractive index of salt solution varies with the mass of the salt added. Okay, so you know that if you increase the mass of the salt, so density is increased. So if mass increased, so the density increase. That means generally refractive index also increased. So you can draw or sketch a straight line with positive gradient. So a straight line with a positive gradient, something like this. But remember, the line should not pass through origin. The reason is the minimum refractive index is 1, which is for vacuum. which is for vacuum, and refractive index can never be 0. That's why the graph should not pass through region. So that's how you can find sketch the graph. C. The relationship between the refractive index n, the angle of incidence θ1, and the angle of refraction θ2 is given by the equation sin θ1 is equal to n sin θ2. Describe the graphical method she could use to determine n. So if you see the given equation, sin θ1 is equal to n sin θ2, and because we need to find n, so you rearrange this equation for n, make n as a subject. So n would be equal to sin θ1 divided by sin θ2. Clearly, this equation is showing that if you have a graph between let's say, yeah, sin θ1 on y-axis and sin θ2 on x-axis, so clearly you must have a straight line, something like this, okay, and the gradient of this graph should be your refractive index. So that's how you need to explain. You need to write your answer that for number of incident and refracted angle, or for various values of θ1 and θ2, students should calculate sine of their angles and then plot the graph of sine θ1 on y-axis, sine θ2 on x-axis, and from the graph, which should be a straight line, the gradient gives us the refractive index. So that's how you can explain, or you can write. The student measured only one pair of angles for each salt solution. The measurement the student recorded for one salt solution were: angle of incidence θ1 is 33 degree, angle of refraction θ2 24 degree. Refractive index was measured as 1.34. The uncertainty in the measurement of the angles was plus minus 0.5 degree. Calculate the maximum and the minimum value of n. So the idea of maximum and minimum value of n, you know that n is sine θ1 divided by sine θ2. So n will be maximum if θ1 is maximum and θ2 is minimum. Similarly, minimum refractive index will be sine θ1 divided by sine θ2. So n will be minimum if θ1 will be minimum and θ2 will be maximum. And the same thing if you recall upper and lower bounds. That's how we find. So now let's just work out. So that means for maximum refractive index, θ1 should be taken as maximum and θ2 should be taken as minimum. So now sine θ1 should be sine of θ1, which is maximum, and θ1 was 33 plus 0.5. So sine of 33.5 divided by sine θ2 should be minimum. So sine of 24 minus 0.5, so 23.5. And after solving this, n maximum will give you 1.384, which is rounded off till 1.38. So this is your maximum value. maximum refractive index, and minimum refractive index is theta 1 should be minimum, so sine of 33 minus 0.5, so it is 32.5 divided by sine of theta 2. Theta 2 will be maximum, so 24 plus 0.5, so 24.5, and then it will give you 1.296. 296 rounded off till 1.30. This is the minimum refractive index of the given values or given solution. Okay, next part, calculate the percentage uncertainty in the student's value of n. So if you need to find percentage uncertainty, remember percentage uncertainty in any quantity, let's suppose quantity x. So how do you find the percentage uncertainty? So uncertainty in the quantity delta x divided by measured value x and multiply by 100, of course, because we have percentage. So we need to find uncertainty in the value of n. So let's see, delta n, which is uncertainty in refractive index, is range divided by 2. That's how we find the uncertainty. And range is maximum minus minimum. So 1.38 minus 1.38 is maximum value and minus 1.3 divided by 2. So your answer will be 0.04. That's how this is your percentage uncertainty. Sorry, it's not percentage uncertainty. This is uncertainty in refractive index. And now percentage uncertainty in n, like this. There's no standard symbol, so that's what I'm writing, percentage uncertainty in n, or if you wish you can exclude this un like this, or you can write something percentage uncertainty in refractive index. So delta n divided by n, meaning 0.04 divided by 1.34, 1.34, and of course multiply by 100 should be there. So percentage uncertainty would be equal to 0.029 multiplied by 100, or just round it off till 2.9%, or you can say this is 3% is percentage uncertainty in the refractive index. Question number 4. A group of students investigated the efficiency of an electric motor when lifting a mass. The students used a joule meter to measure the energy supplied to motor to lift a mass a distance of 75 centimeter. They repeated the experiment twice before increasing the mass. So mass, electric motor, joule meter 0.57, and keep these numbers in your mind. 0.57 joule and 75 centimeter is the height covered by the mass when lifting by the motor. They calculated the change in gravitational potential energy of the mass and the mean energy supplied. Their results are shown in the table below. So mass in kilogram, okay, 0.02, 0.04 kilogram. Change in gravitational potential energy is given in joule. Energy supplied read by joule meter in joules. So 3 trials and mean values. Criticize the result. So you need to see the table and try to find some error if you think that there are some, and that's what the meaning of criticizing results. So now if you see in the first column, you see we have three significant figures. 3SF, and then 2SF. That means inconsistent significant figures they used in gravitational potential energy column. And also, if there is any anomalous result, I don't think so. Again, you see the mean value column 0.573, 1.12, and 1.7. So 2SF and 3SF, and then again 3SF. So you have again inconsistent significant figure. So it should be because this is the 3SF values that the meter is showing everywhere. So meaning the mean value should have at least three significant figures here. So that's what you can write in criticizing your result for 2 marks. So for first column, inconsistent, it should have 3 SF. Part B, complete the last row of the table. So if you see the last row, this is change in gravitational potential energy. Again, a straightforward calculation, mgh. So m is the mass, which is 0.12. You can see here. I'm just doing calculation underneath the column, so you can see the results. So 0.12 kilogram. G is 9.81 times height, and height is 75 centimeters. So 0.75 centimeter. If you multiply these number, so you can have the value in the first column. Similarly, these are the mean value. The last column is the mean value. So you just add these three numbers and then divided by 3, and because as there are no anomalous readings, so you include all the 3, so divided by 3, so you have number here, and your final answer should be 0.88 joule, your change in gravitational potential energy, and the mean value is 3.34. Part C, plot a graph of change in gravitational potential energy on the y-axis against mean energy supplied on the x-axis. So here is a graph, and these are the values of mean energy supplied in the first column, and change in gravitational potential energy in the second column. So you can take mean value on x-axis and change in potential energy on the y-axis. So that's how your axis should look like. So these are the range 0.5 to 3.5. If you see your mean value starting from 0.573, and the y-axis value 0.1 to 0.9, you see here, you can easily plot all the values. And if you plot corresponding values, so you can have 6 points as you have a 6 reading. So these are your 6 point. And then you will have to, whenever you are plotting graph, don't forget to plot line of best fit. Line of best fit is the line that is equidistant from all the point, or passing through maximum points, or equal, all the points should be equally distributed. So this is, you can think, a line of best fit. Determine efficiency of the motor. This is your part D. And for efficiency of the motor, if you see your graph is a change in potential energy on the y-axis, and mean energy supplied is on the x-axis. And remember, this mean energy is supplied. That means this is your input, and this one is your output. And if you recall the efficiency definition, output divided by input gives you efficiency. That means you just need to find the gradient of the line. If you find the gradient, this gradient will be efficiency of the motor. So for to find the gradient, of course, we are going to choose 2 points to draw a triangle as big as possible. So these are the 2 points you can choose on this line anywhere. So I am choosing these 2 points. If you see here, this is the 1 point and another point, and you can draw a large triangle. You can draw a vertical line and a horizontal line to show a triangle, and then the corresponding points. So these are the corresponding points of your triangle, and you can draw something like this. And then you will have to find your gradient. So gradient will be equal to y2 minus y1. That means 0.8 minus 0.2 divided by 3.05 minus 0.75, and this gradient will be equal to 0.261. That means after multiplying by 100, so efficiency E would be equal to 26%. This is the efficiency of your motor. The students repeated the experiment with a much larger mass and determined that the efficiency of the motor was decreased. Describe how they should collect and use data to determine the mass at which the efficiency starts to decrease. So if you go back to your previous slide or previous graph, you see you have a straight line throughout. That means efficiency is constant throughout in this given interval or given masses, but efficiency decreases with the mass. So what students can do, they keep increasing the mass until they find that at some higher mass, they will find that the curve starts decreasing. If curve start decreasing something like this, that means the efficiency is decreasing because gradient is decreasing. So once they realize that at some greater mass, the straight line starts decreasing, gradient starts decreasing, and then they keep adding with a small fractional of masses to get exact exact mass at which the efficiency start decreasing. So they will have to figure out the small increment of the mass at the moment when the graph just starts decreasing or curving, something like you can say. Question number 5. A photograph shows a bungee jumper. The bungee jumper falls through a large distance and is then decelerates by the bungee rope. This is a bungee jumper and the rope. Okay. For safety, a bungee rope needs to be tested to ensure it can withstand the stress applied as it decelerates the falling bungee jumper. One bungee rope has a diameter of 2 centimeter. The manufacturer states that the rope can withstand a maximum force of 8,000 Newton. Part A is a teacher is given a sample of the same material with diameter of 1 millimeter. Justify the teacher's decision that it would be safe for her students to determine the breaking stress of the sample. Okay, so we have a actual bungee rope with the diameter of 2 centimeter and the sample of diameter of 1 millimeter, and we need to justify teacher's decision. So we know that it doesn't matter what the size of the sample or material is, there is a quantity that remains same when we have some extension or some strain. So stress is the property that remains same no matter what the size of the sample is. The only condition is the sample should be made of same material. So the sigma or stress will be same in both of the sample, original and the given sample. So you say that F's and you know, of course, sigma is F upon A, force upon area. So clearly you can say that F1 upon A1, which is I'm considering stress of sample 1 or original row, should be equal to F2 divided by A2. So I know that I have the maximum force at 1000 Newton, which is F1, and A1 I can figure out from this, and then I just need to figure out F2 whether it is within the range or not. So F2 would be equal to F1 A2 divided by A1, and you know that area A is pi r square or pi d square by 4. This is formula for area. Why am I using this pi d square by 4? Because diameters are given, so I just don't want to go in the detail of radius. So pi d square by 4. So clearly you can say that F1 into A2 will be equal to pi d1 is, sorry, not d1 because it's area 2, so d2 square by 4 divided by A1. A1 is pi d1 square by 4. Clearly pi, 4 and 4. So you say that F1 d2 square by d1 square. So F1 is 8000 and d2 is diameter of the second sample, which is 1 and 1 millimeter. So I'm just taking its 1 square divided by d1 d2 is 1 and d1 is 2 centimeter. So it is divided by 20 millimeter because I took 1 in millimeter. So the first diameter should be in millimeter. So it's 20 square. You don't need to convert in meter because we have a ratio of d2 and d1. So millimeter will get cancelled. It doesn't matter. Clearly, if you solve this relation or this equation, so F2 you will find is 20 Newton. And now you know it is quite less, so it is sufficient. That's how you can say yes, indeed, teacher decision is right, it is correct, it is safe because of the small values of force. Again, I did this question in every detail. You can skip a lot of step if you are good in maths, so you can skip a lot of step. Don't think that for 2 marks you will have to show every steps here. It's your choice. Part B, to determine the breaking stress, a student used 100 grams slotted masses hung vertically from the sample. The maximum mass that the sample could hold before breaking was 1.9 kilogram and the diameter at that moment was 0.95 millimeter. The manufacturer gives the breaking stress of the rope is 2.55 10 to the power 7 Pascal. Determine whether whether the students' result support the manufacturer value or not. So again, you will have to figure out stress calculated by the students, and then you need to compare whether it is within the range or not. Okay, so let's just figure out the stress, which is sigma is equal to force upon area, and in this case, because the students is hanging mass, okay, hanging mass vertically, that means this sigma is basically this force is basically weight of the hanging mass. So mg divided by area, and area is pi d square by 4. So I can say that I can send 4 on the others for the in the numerator, and then you can say that 4 into m, and mass which is hung is 1.9 into g, which is 9.81, divided by pi is 3.14 into d square, and diameter is 0.95 millimeter. So 0.95 into 10 to the power minus 3 d square, that means square. And then you can find sigma. So sigma is 2.62 into 10 to the power 7 Pascal. Clearly you can see 10 to the power 7, 10 to the power 7, they are the same, so you can compare just these number. If you wish, you can compare the whole number with power, but you can say that since 2.62 or 10 to the power 7 is greater than 2.55 10 to the power 7. So of course the manufacturer statement, yeah, so it supports, yes indeed it supports. You just write a statement. Thank you very much. I hope you understand. Have a nice time.